push that rock here with Simpson math. Go Frogs. So we're going to talk about improper integrals. Improper integrals. And this is an introductory video, but it's dealing with one where there's an unbounded domain. And the key to the unbounded domain is this limit of integration that has infinity in it. It could be down here, it'd be negative infinity maybe, but let's draw a graph of the area implied by this seemingly definite integral here. If I graph this function here, y equals 1 over 1 plus x squared, put in 0 for x, you get a 1 for y. So I'm going to use another color. And if I put in 1, well then I'm going to get 1 squared is 1. I'll have 1 over 1 plus 1, so 1 over 2 is a half. Notice if I put in negative 1, I'll get the exact same thing. So whenever you have when the variable is being squared, it's going to be what we call a symmetric about the y-axis, so it's an even function. Now when I put in 5, I'll have 5 squared is 25 plus 1 is 26. I have 1 over 26. It's a really small fraction. In fact, on this scale, it'd be kind of hard to see the difference between it and the x-axis, but of course there is a difference. Now, as I put in increasingly large x values, that difference between the output of the function and 0 gets smaller, but there's always a difference. With a little bit of derivative work and second derivative work, I'd see that it's concave down for a little while in here and then concave up after there. There's some inflection point about there, but all that's not all that important. But we do need to have an accurate enough graph that we can shade the area. So I should have blown this up now that I think about it, but we're going from 1 to infinity, so I'm going to shade this area, and we see, well, there's an infinite area, because even though this is going to be so small that on my scale you won't even be able to see the difference between 0 and the curve. But as you go further out, you have to blow it up more and more and more, but there's always is a positive difference between the output of the curve and the x-axis. But it's asymptotically approaching 0 as the x values grow very large, go to infinity. So this is an improper integral because the area is infinite. Okay, so how can we compute the area of infinite area? I mean, isn't it just infinite? Well, it turns out that it's not. That this infinite area actually is not infinite, but fits in a finite space. Wow, oh, that's weird. How do we go about finding out if that's true or not? By the way, if it is true, if the area, let's call the area A, if the area is some finite number, we say that the area is convergent. It converges to a finite number, and we just say that it equals that number. If, however, it doesn't, well then we say that it's divergent. So in other words, the area is just going to do what we would think it would do naturally, just expand. The further out you go, the more area is added in, and it just keeps getting bigger and bigger and bigger, and it diverges, or is a divergent improper integral. So there's some terminology there, convergent and divergent improper integral. Now let's just do this example. So the way to do this is, first of all, show the graph. Look, if I'm grading your work, I want to see this graph first. If I don't see that graph, I'm going to stop grading. Show me the graph first. And show me a good enough one that's at least this good. Okay, so we have the graph. So now I'm ready to solve it, but I realize that this is not a number. And to do a definite integral, that needs to be a number. So what I'm going to do is set up a limit. And I'm going to put a dummy variable in up here. So I'll put in, let's see, we'll use A for Austin Matson. That's a great dummy variable. And we're going to say, any strangers watching this video, Austin is totally cool with me saying that. And so anyway, maybe I shouldn't have said it just because strangers watch this video. Anyway, we're going to put A, and we're going to say A is approaching infinity. And then we're going to have this right here. And we're going to go like so. So, oh, and don't forget the lower limit of integration. So we have our dummy variable that's representing the upper limit of integration, but we're going to find the limit as that upper limit of integration expands out to infinity. Now, now I'm ready to integrate. So I'm going to integrate first. I'm coming inside the limit, and I'm doing this first. So we're going to do that, and the way we do that is we get the antiderivative, which is arctan of x. And then we're going to go from 1 to the upper limit of integration. And then we're going to use the fundamental theorem of calculus, the evaluation part. This says that you evaluate the function at the upper limit. So I have arctan of a minus you evaluate the function at the lower limit. So arctan of 1. Now, arctan of a, well, I don't know what that is. But we're going to compute the limit of it as a goes to infinity. Okay? Now, over here, I can bust up limits, so I'll bust it up. I'm taking the limit as a goes to infinity of arctan of 1. But arctan of 1 is pi fourths. And the limit of a number is a number, so I have minus pi fourths here. But what's this limit? Well, we need a graph. So we need to look at the arctan function as the inputs go to infinity. So we'll do that over here. So the arctan function, hopefully we know, has these asymptotes here, and we have a curve that's doing this. And at 1, if this is 1, then this should be pi fourths, the output of pi fourths. But the question is, here's our input axis, which our variable is a, and here's our output axis, and our function is arctan of a. What happens to the outputs as the inputs get infinitely large? Well, they're approaching this asymptote up here, which is pi halves. So this function, this limit is headed towards pi halves. And so we get pi halves minus pi fourths, which of course is pi fourths. So we say the improper integral converges to pi fourths. Math made simple. Simpson math.